For this video, it's going to be important that you already have a solid understanding of exponentials and logarithms, that you know the logarithm rules like the power rule, the product rule, the quotient rule, any exponent rules that you should know from grade 11, and of course the solid background for solving equations and isolating variables. I'm going to start you off. It's not going to be easy to start off because I'm sure we're going to have a lot of practice with the easier ones. So I'm going to give you some strategies to solve something maybe a little bit more complicated. So let's start off with, let's say, 14 to the power of 3x minus 6 is equal to, I'm just making this up as I go along, by the way, 13 times 27 to the power of 2x plus 4. Looking at this, the first thing I notice is the variable in the exponents. I think, okay, well, my first strategy is going to be, let me take the logarithm of both sides. I could take the log of any base. I'm just going to take the log base 10 because I know everyone's calculator has log base 10. So let's just say the log base 10 of, for the left side, which is 14 to the power of 3x minus 6, is equal to the log base 10 of this whole side, 13 times 27 to the power of 2x plus 4. Now pause the video here and see if you can at least do the next line. If you could solve the whole thing, excellent. Of course, check your answer and then come back to here. But at the very least, see if you can get the next line right. On the left side, we've got log 14 to the power of 3x minus 6. If I don't say the base, then we just agree that it's the base 10. So the power rule tells us that that's just going to be 3x minus 6 times the log of 14. On the right side, though, be very careful because taking the 2x plus 4 to the front would be a mistake because this is not the log of 13 times 27 all to the power of 2x plus 4. It's a log of 13 times 27 to the power of 2x plus 4. Only the 27 is being raised to the power of 2x plus 4. The power rule doesn't apply here, but we are taking the log of 13 times something, right? So this would be the product rule. Log of 13 plus the log of 27 to the power of 2x plus 4. And now that second one, the log of 27 to the power of 2x plus 4, now we can use the power rule there. So a big mistake would be to take that 2x plus 4 and bring it to the front of the whole thing. But that 13 has nothing to do with the 2x plus 4, so you have to be very careful of that. So we're going to use some basic algebra skills here. So we're going to say the next line is going to be 3x times log 14. You have minus 6 times log 14, that's distributing, is equal to log of 13 plus, we distribute again, 2x times log 27 plus 4 times log 27. Let's bring everything with an x to the left and everything else will move to the right. First term we have 3 times x times log 14, so that's 3 log 14x. We also have 2 times log 27x, that will be negative 2 times log 27x on the left, and everything else goes to the right. Okay, we got common terms on the left, so we'll put those together. Now we'll isolate x by dividing both sides by the same thing, and put that in our calculator, and we now have our answer. Now with logarithms, it's super important to check your answers. Sometimes, that we might accidentally take the log of a negative number, which you can't really do. So at the end, if you have, no matter how many answers you have, you want to plug it back in to see if it actually works in your equation. So let's check it out. Throw this number into there. Now I don't actually write this number that you see, 23.826995348. That's actually rounded. I keep the whole thing in my calculator to plug it in. I'm going to plug it in on the left and on the right, make sure they equal the same thing. If it's too small or too large of a number, instead of plugging in the whole thing, I would just plug it into the left side and then subtract one term at a time from the right side and basically bring everything to the left and put the whole thing in and make sure that it equals 0. And that's what I'll do here. I'll bring everything to the left, plug this number in. Hold on a second. right, and it equals 0. Perfect. All right, let's try another problem. Let's clear the screen here. Let's try 5 to the power of x equals 3 to the power of x plus 1. All right, here again you have your variable in your exponents. So my strategy is obviously going to be to take the log of both sides. Now the question is, do I take the log with a base of 5 or do I take the log of a base with a base of 3? Right, so I guess we're going to, let's try both of them and see which strategy seems to pay off, which one seems easier. So on the left here, we'll take the log with a base 5 on both sides, and on the right side, we'll take a log with base 3 on both sides. All right, step 1 on both sides. So on the left, you've got log base 5 of 5 to the power of x. Well, these are inverses of each other, so we're just going to say that equals x. On the right side, the same thing, but it's on the other side of the equation. So log base 3 of 3 to the x plus 1 will just equal x plus 1. All right, next I see immediately we have a log with a power inside it. So we're going to use the power rule. On the left side here, the x plus 1 comes down, and on the right side here, the x comes down using the power rule. You should probably take note, there's a small difference between the two sides in that on the left side we had an x plus 1 that came to the front, and so we absolutely positively needed to put brackets around that because we don't want just the 1 to multiply the log 3 base 5. We wanted the x plus 1 to multiply, so the x has to multiply by it and the 1. Whereas on the right hand side there was only an x that came down, so it's not ambiguous. You don't need brackets. You know that it's x times log 5 to the base 3. And that's also why this next step is going to be a little bit different for both of them. On the left side here, you're going to have to use your distributive property. So x equals x log 3 to the base 5 plus 1 log 3 to the base 5, or just log 3 to the base 5. And on the right hand side, you don't have to do that. You don't have to worry about that distributive property. All right, let's gather up all of our terms with x and put them on the left, and all the terms that don't have x and put them to the right. In both scenarios, you'll have to factor out an x. In both scenarios, divide both sides by whatever's next to the x so we can isolate the x. And now just stick it into your calculator. Make sure you attend to orders of operations and you do it properly in your calculator. If you do have a problem with log base 3 or log base 5 in your calculator, just remember that the log of 3 base 5 is the same as log of 3 divided by the log of 5 in base 10. Or log of 5 base 3 is obviously log 5 divided by log 3 base 10, or any other base. All right, so I did them both in my calculator, and I got an answer of approximately 2.15066. And I got the same thing for both of them. Thank God, because if it gave us two different answers, then we know we made a big mistake. Now, it's very important that we plug this back in, because when you're dealing with logarithms, remember, there's certain numbers that just don't work. And so when you're dealing with variables, you have to make sure that you don't do a step where you do something illegally accidentally. So you need to plug that number back in and make sure it actually works. So let's do a check. All right, to check, it's probably sometimes easiest just to bring everything to the left and then make it equal to 0. And then when you plug everything in, make sure that yours equals 0 instead of doing a calculation twice. But either way, it doesn't really matter. The problem sometimes is if you don't do that, the problem is sometimes the numbers are very, very small, and it's hard to tell if the two sides are equal. But when you put everything to the left, it's easy to tell if it just equals 0. All right, so I'm just going to do 5 to the power of x minus 3 to the power of x plus 1 equals 0. I'm going to plug in my value that I got, so 5 to the power of 2.15066. I'm not actually plugging that in, I'm plugging the real value that I had saved in the memory of my calculator, minus 3 to the power of 2.15066 plus 1, and that is equal to 0. Yay, so that actually works, so therefore my answer is a valid answer. I'll finish off with these two equations. They're very similar to each other, so I figured I'd do them at the same time because the steps will be very similar. So if you notice, both of them have logs with a base of 2. So we're going to end up using the inverse operation, which is 2 to the power of x, or 2 to the power of something. Notice I raised the left side and the right side as an exponent. So I did 2 to the power of the left side equals 2 to the power of the right side. But I didn't just do part of it. If you're going to do the same thing to both sides, it's the entire side. So I have to raise the entire side. 2 to the power of the entire side. 2 to the power of the entire side. You can't break it up into parts because it's not saying that, the one side is equal to part of the other side. It's saying that the entire side is equal to the entire side. So whatever you do to one side, you have to do to the other. On the left side, you'll notice that you have 2 to the power of log with a base 2. Those are inverses of each other. So on this one, you're just going to get 14x plus 4. The 2 and the log base 2 cancel. On the right side, though, we've got a little work to do here. We have 2 to the power of a plus b. So our exponent rules tells us that that is equal to 2 to the power of a times 2 to the power of b. So this is 2 to the power of 3 times 2 to the power of log x minus 1 base 2. And now you have these guys do cancel each other out, and you end up with x minus 1. And exact same steps on the other side here. 2 to the power of 3 is 8. Let's use the distributive property. So the right side is 8x minus 8 for both of these equations. Pull all the terms with x to the left and everything else to the right. Add like terms. Divide both sides by the coefficient in front of the x. And voila, we have our answers, right? Well, not necessarily. As I've told you before, and as I've told you all year long, we need to check our answers, especially with logarithms. Logarithms sometimes have answers that are invalid. So let's check it out. On the left side, we'll plug in -2. On the right side, we'll plug in x equals 4, so that we're doing both problems at the same time. And we will check. I like to bring everything to the left to make sure it equals 0. And I think that just works nicer, just in case you get problems where your calculator can't handle the number because it's too low or because it's too high. It just makes life easier on me. The equation on the right didn't give me any trouble at all. I got log 24 base 2 minus 3 minus log of 3 base 2, and that does indeed equal 0, and we are good to go. On the left, though, it didn't work. My calculator keeps spitting out that it doesn't like the numbers I'm giving it. And that's because if you look, we have log of -24 base 2. But what do we know about logs? Is that even a possible thing? No, it's not. So our answer of x equals -2 is actually inadmissible, and there's no possible answer for this logarithmic equation. Now, what went wrong? Well, all the steps that we took in here, we did assuming that we would never take the log of a negative number. But we had a variable, we had x, so we really didn't know if we were taking the log of a negative number or not until we got to the end. Now, if you look through this one on the left, you have here the log of x minus 1 to the base 2. Which sounded fine when we didn't know what our x value was. But as soon as we found out that x is -2, well, what did we just do? We just did the log of -3 base 2, and that doesn't exist. So the rest of our equations, the rest of our work was no good because we made an assumption that was incorrect. We made the assumption that 14x plus 4 is equal to 2 to the power of 3 times 2 to the power of the log of x minus 1 to the base 2. That's not true because the log of x minus 1 to the base 2 doesn't exist when x is -2. So for that value, it didn't work. And that's also why it didn't work in our original equation. Now to the right, x is equal to 4. So that wasn't as much of a problem because log of 3, so 4 minus 1 is 3 to the base 2, is a valid answer. So this one was valid all the way through, and as you saw, we did get our answer. So it just kind of reinforces the idea that you have to check your answers in the end. There's no way that, like if I was doing a homework really quickly, it's not really that obvious which one would have been a possible answer. You have to go back and you have to check your answers.